Press escape. We don't want to do that. It says recording. All right. That's too dang bright. Turn off one of these. It's ridiculous. We'll turn on one of them. That's enough, maybe. Okay, well, let's see if we got any customers here. I don't have anybody yet. Just me, I guess. Well, I'm going to call my IT person here. Hey, we've got a student, Nicholas. ¿Cómo estás? How are you doing, Nicholas? Have I muted everybody? Unmute Nicholas and say hi. Well, Nicholas is busy. He hasn't.
No, I got you.
There
Good
you
morning.
are. Yeah,
Yeah, good morning.
Good morning. You're my first student this morning so far.
Well, it's an honor.
Yeah. Yeah, that's how I'd like to get to know my students. How old are you, Nicholas?
I'm 39.
Holy
Yeah.
cow, you're an old guy.
Yeah, I'm old.
Well, that's good. How does it feel to be competing with all these young, smart students around you at school? It's kind of intimidating, isn't it?
Yeah, I was about to say that word exactly. It's at times it can be intimidating.
Yeah. Well, just think of what it would be like for me. I'm 77. So,
well, you were smart and you did this. You did this when you were young.
yeah. Yeah.
I waited too long till I decided to do it.
Well, what was it? Grandma Moses started painting when she was 80 something. So
I guess there's examples that I can,
yeah, good for you. Yeah.
take some
Hey,
inspiration from.
we got some more customers. Ashley and Brian just showed up. So we're doing great. Yeah. Well, it's a pleasure getting to know each one of you. I like to associate your face too, but see, I don't know what you guys look like unless you, what do they call it, pin yourselves.
Well, I'm going to meet you this afternoon for.
Oh, you're into physics. Oh,
yeah.
Good. Yeah. Now, I'm going to wear a mask.
Yeah, me too.
Yeah, I think in fact,
You have to, don't you?
We have to wear masks.
Yeah.
But how am you going to understand anything I say with a mask on? It's sort of muffled, you know? Well, what if I stand far enough away from you guys, like 8 or 10 feet away from you? I could take my mask off and say a few things, you think?
Yeah, I think that'd be okay.
I think it'd be okay.
Now, I mean, you do that. That's how you do it everywhere else.
Yeah, I think so. Yeah. Okay, well, let's see. I need to get my pen myself, I guess they call it. There we go. Yeah, there I am. And I wonder if you could read. See, it's supposed to say the date on there. It is. There's the date. It's the 20th. Okay, good deal. Yeah, that's pretty good. Not bad. Now let me, if I turn on another light, let's see. I want this to be where you guys can read it. What if I turn that one, this one here on? That just might work. Is that any better or worse? What do you guys think? There's a glow. We don't want that stinking glow. Just a minute here. I don't think it's too bad with just that one on. That's not bad at all. We'll just leave that alone. Okay, well, we're going to get started, I think. Let me make a note to my IT person. All right. We are in Strength of Materials. And I'm going to look at my syllabus here, or my schedule, and see what we're supposed to do today. This says stress and internal loads. Okay. And well, external, you can't do internal loads unless you have the external loads. So we're talking about there's external loads. And there's internal loads. And guess what? In order to find the internal loads, you first have to find the external loads, and then you can get the internal loads. And then once you get the internal loads, you can get the stresses, because see, the stresses, there's two kinds. I was telling you that the last time. This is normal stress and that's shear stress. They come from the internal loads. There's an equation for normal stress that goes like this. And you see that N right there? That's an internal normal force. And then shear stress goes like this. See, you're dividing by the area. And you see that V right there? That's an internal load. That's the internal shear force. To find the stresses, which are all important, you've got to get the internal loads. Now let me show you the difference between forces and stresses here. Let me see who I've got right now. We got a good crowd here. We've got Nicholas, Ashley, Ben, Brendan, Brian, Mohammed, and Julian, and Darren, and Chase. We got a great group here. Okay, well, let me demonstrate the most important concept in this class is stress. And it comes in different types. See, this here is called normal stress. The word normal refers to being perpendicular to a surface. And then this is shear stress. Shear stress is not perpendicular to a surface, it's parallel to a surface. Normal is perpendicular, shear is parallel. Here's your symbols. That's a little secret symbol for perpendicular, and there's the little secret symbol for parallel. Any questions so far? Okay, well, let's do some problems and try to show you that. I was going to show you though about why stress is so important. I've got my what they got? Swiss Army knife. I've got my Swiss Army knife here. I'm sure you guys have all seen Swiss Army knife. Now, if I take this Swiss Army knife and I just hold it on my hand like that, that doesn't hurt. That doesn't hurt my palm of my hand at all. Of course, if I let go, it'll fall. I have to kind of hang on to it there. But it's not hurting. It's not hurting my hand or my finger. I could put it on my finger. Here we go. Yeah. Can you guys all see that? I've got the Swiss Army knife. It's on my finger. It doesn't hurt my finger at all. Because there's a lot of area right down there. Now, if I turn it around like this, though, maybe this isn't too smart. But see, here, it's the same force, but it's starting to hurt because the area of the tip of that blade is very, you see, it's a very small area, and that makes the stress very big. Well, that's enough of that. I've got, you guys can't see it, but I've got kind of a hole there in my, yeah, you can see it. There's sort of a hole right there. Well, it didn't punch a hole in my finger, but it's a little bit uncomfortable. You guys probably already understand all that, but see, stress depends on the area. And if the area is small, you know how fractions work. If the denominator is small, it makes the fraction big. And so the stress gets very big if you make the area very small. Same with the shear stress. Okay, well, great. Any comments or questions? We'll work a problem. All right. I thought we could do problem 1-9. It's not on your homework. I hate to do your homework for you. Only I don't guess that would really hurt anything. But 1-9 is not on your homework. I see your homework. Your homework is 178 and 186. So it's on the course schedule. Well, if you click on Unit 1 in Blackboard, it'll tell you your homework. And it'll tell you when it's due. It says it's due the 28th. That can't be right. No.
111 and 114.
Yeah, it's F111 and F114. It's due the 23rd. Well, what's the 23rd? Just a minute. Is that Saturday? I've got a calendar here. Yeah, 23rd. No, that's Sunday. Sunday night at midnight, your homework is due. You can click on the link on Blackboard. You'll have to take a picture of your homework or use a scanner or some of my students have what they call a CAM scan. Does anybody have a CAM scan?
I do. It's like a app on your phone. Cam
It's
Scanner. You
just
just take a pic and it formats it for you or cuts it down to just a paper.
fantastic. Now tell me your name.
Braxton.
Braxton, thank you for sharing that, Braxton. I bet a lot of the others have the same, or they can get that app. Can't you just download it, Braxton, somehow?
Yeah, it's on the App Store. I'm pretty sure it's on Android too, but
Do you have to pay money to get that app, Braxton?
no, it was free for me.
Oh, I like that price. Yeah, that's good. Okay, we're going to do 1-9 now. Let me find it here. What page is it on? Page 8. It's on page 18. Okay. Now, if I was doing this for homework, I would get some engineering paper, or else some cheap graph paper, and I would draw this to scale. I need you to draw a diagram. Now here it goes. Let's see if I can do this. This thing is 6 meters long. Why don't I use inches? That'd be good. Let's go with inches. Here we go. 6 inches. Yeah. Okay, now there's our beam, and there's going to be a force up here. Why don't I put my forces in red? That would be good. Let me find some red here. Now see, these are going to be external forces. There's going to be an external force there. I don't know if they're going to be equal. In fact, I think it looks like this one's going to be bigger. And they gave them names. They're going to call that A and B. And then they have a triangular force distribution. So let's put that on there. See, they've got a force distribution. And over there on the end, it's 4 kilonewtons per meter. Okay. Now what we're going to do is we're going to write the resultant of that distributed load. And hopefully you guys already know this, but the resultant of a distributed load is equal to the area, and that's a triangle. And this distance here is 6 meters, and that distance there is 4. And they taught me in school many years ago that the area of a triangle is 1/2 the base times the height. I've got 1/2 the base. The base is 6 meters. The height is 4 kilonewtons per meter. And this will give me the resultant. I can do that in my head. I get 12. The meters cancel, and so you get 12 kilonewtons. Now, the resultant of a distributed load, you already knew this, but I'm reminding you, it goes through or passes through the centroid. Do you remember that the centroid of a triangle, it's something about 1/3. Let's ask one of our students and see if they remember that. We'll just ask somebody. Hey, Ben, unmute and tell us, where do you put the centroid on a triangle like that?
On a triangle, it's 1/3 from the largest side.
You got it. Ben's got it. It's 1/3. So let's see, if this is 6, divided into 3 pieces here, that'd be 2 meters, 2 meters, 2 meters. That makes 6 meters. So here you have it, guys. The resultant, I'll call it R. It's 12 kilonewtons. Okay, great. It's 1/3 from the bigger side and 2/3 of the way from the smaller side. And hopefully you guys remember doing that. And now the next step is to find the A and B. Now to find those, you have to use these equations, the equilibrium equations. And of those, this is the most important. Taking moments is very powerful. So I'm going to take the moments about point A. We'll call this point A right here. And if you take the moments about A, you get, well, you get negative 12 kilonewtons times 2 meters, we decided, plus B times 6 meters equal to 0. And if you solve that, you'll get B is 4 kilonewtons. We just figured out B. B is 4 kilonewtons. And if you got 12 here, and that's 4, this has got to be 8. So A is 8 kilonewtons. You get that from the sum of the forces. 8 and 4 add up to 12. 12 going up, 12 going down. Sum of the forces is 0. But I want to ask one of my students, I picked on Ben there. Let me go to my friend Nicholas. Nicholas, how come this moment here, this 12 kilonewtons times 2 meters, how come it's negative, Nicholas? How come
it's clockwise relative to A?
That's the answer. The answer is it's clockwise. See, that 12 kilonewtons would try to spin you clockwise about A. You can see that. But B here tries to spin the whole thing counterclockwise about A, so that's plus. Counterclockwise, let me refresh your memory. Counterclockwise is plus, clockwise is minus. So you know what we've done? We have found the external loads. When you work your problems in this class, you got to find the external loads. But that's not how you get at the stresses. Remember, to find the stresses, we need the internal loads. Okay, well, let's see what they want us to find here. Let me read this. We're doing problem 1.9. If you just tuned in, it's on page 18 in your book. And what am I looking? Oh, they want us to find the the resultant internal loadings. Oh, we're not going to find the stresses. They don't care about the stresses. We'll get to that later. They want to see if you can find the internal loads. Now there's 4 kinds of internal loads, and they want us to do it at point D. Okay, well, where is D? Well, D is right here. That's point D. And they say it's 1.5 meters from the end. Okay. 1.5 meters from the end. They want the internal loads. Now let me list the internal loads for you. We don't need any of this stuff here. This is all wonderful, but I think we understand it okay. There are 4 kinds of internal loads. Now the book sometimes calls these something else. It calls them resultant or reactions. Internal, there's different names for these. Internal reactions. So see, what they are is reactions to the external loads. Some books call these the resultants. No, that's not right. Internal, yeah, some of them do. Resultant. Resultant loads, there we go. Different names for it, but there's 4 of them. Is there room for me? Yeah, there's room. Okay, now I'm going to ask one of my wonderful students here if they know the names of those 4 different kinds of internal loads. Let's go to my friend Ashley. Ashley, do you know what they're talking about, the 4 different kinds of internal loads?
Normal,
Yep,
shear,
that's right.
bending moment,
That's right.
and torque.
You got it. These are the 4 things, and this is what they wanted. And we're going to find it for them. Now, this is a force. These first 2 things are forces. And so in this problem here, they're going to be in this case, kilonewtons. But these things here are moments. And they're going to be in kilonewton meters. Moments are in Newton meters or kilonewton meters. But there is no torque. See, torque would be if this thing was being twisted along its axis. See, torque is a twist along the axis. See, the axis of this beam here goes like this, and torque would have to twist that axis. And there is no torque, so we don't need to worry about the torque. You can forget it. But we do have these others. And I take that back. You know what? There aren't any normal forces either. All there is shear forces and bending moment. I don't see any stretching or compressing going on. No, I don't. No, I don't. Now, to be perfectly honest with you, there is some normal forces in that beam, but we're going to study those later. because the beam bends. That beam is going to deform a little bit. Here, I'll draw you a picture of it. It's going to go kind of go like that. Now, I'm exaggerating this like mad. You probably couldn't see any of this deformation going on with your unaided eye. But can you see that if you have this force going down and these forces going up, it's going to make kind of a little dip in that beam, isn't it? Yeah, and it will deform a little bit. And you will discover that you will have tension on the bottom and compression on the top. So you will have normal forces, but we're going to pretend that we don't know anything about that. And so I don't think we need to worry about that. I bet the answers in the back, when we look them up, they'll have a shear force and a bending moment, and that's all we need to worry about. We're going to find those now in a minute, unless you have a comment or question. Okay, well, we're going to find the internal loads. Here goes. Let me make a little room here if you like that and understand it. That was all interesting about the resultant of a distributed load is equal to the area, and it goes through the centroid. But now we're going to find the lost my train of thought. We're going to find something. Let me get a drink of water and I'll remember. Oh yeah, we're going to find the internal loads, the two of them we're interested in, at point D. Now to find internal loads, you have to break the structure into parts. Let me write that. To find internal loads, you have to break the structure into parts, or you could say you have to break it into sections. You have to analyze the sections or the parts. So I'll just say you have to break it into parts. That'll do the trick. And then what do you do? Well, you have to start all over. You have to draw your diagram of the part that you're talking about. Then you have to find all the external forces on your part. Then what? Well, then you're done. Okay, well, let's do it. Now they want us to do it at D. So what you do is you section this structure at D, and we're going to cut it with a pretend virtual chainsaw. There we go. Now we're going to redraw that body. Here's D, and here's B. And it just has a little part of that distributed load there. See it? There it is. I need to know what this value is right here. Well, see, that's 4 there. If it was halfway in the middle, it would be 2. all the way at the end, it's 0 kilonewtons per meter. If you were smack dab in the middle, it would be 2 kilonewtons per meter. If you want to find out what the distributed load is there, and by the way, they use a little symbol W in this book for distributed load. I need to know what that W is. Well, 1.5 is 1/4 of the way to 6, isn't it? 1.5 is, it's 1/4, isn't it? So what's 1/4 of 4? Oh, hey, I can do that. I can handle that. That value right there is 1 kilonewton per meter. Now see, what we're doing is we're starting all over again. We're drawing our diagram and we're finding all of the forces. Well, we already have a force here on the end of 4 kilonewtons. That's 4 kilonewtons.
Professor Griffin,
Yeah, go ahead.
is it 1 kilonewton per meter? Is it just 1 kilonewton? Like, is that the resultant?
No, it's 1 kilonewton per meter. See, this is 4 kilonewtons per meter. If you were right in the middle of this distribution, it would be 2 kilonewtons per meter. At the very end, it's 0.
Oh, okay.
Tell me your name.
Julian DeCarlo.
Thank you, Julian.
Yes, sir.
Now, we're going to have to figure the resultant of this little distributed load here. And I forget what excellent student informed us earlier, but you go 1/3 of the bigger side. Well, what's 1/3 of 1.5? That'd be 1/2 meter, wouldn't it? And so it's right. This resultant here, now this is a different resultant. This is just the resultant of that little distributed load there. And we're going to figure out what it is. Well, it's the area of the distributed load. It's 1/2 the base, and the base is 1.5 meters, and the height is 1 kilonewton per meter. I can do that. Now, if you do that, I get 0.75. I get 0.75 kilonewtons. Double check me on that. We just figured out this resultant force. Okay, guys, the sum of the forces has to be 0 on this part or section. If you got 4 going up and 0.75 going down, then it seems to me you're going to have a shear force going down. How big? How big should it have to be in order for the sum of the forces to be 0? Go ahead and just tell me, somebody. See, we got 0.75 going down. I should draw that kind of small. It's pretty small. And we have 4 going up. What's this going down? I mean, they have to add up to 0, right?
3.25.
I love it. I love it. It's 3.25 kilonewtons. You know what? That's the shear. Well, great. We figured out what the shear is. Now, what's confusing about shear is they define shear on a left-hand member. If the shear is going down, they say that the shear is positive. And if you have a left-hand member and the shear is going up, they say that's negative. But this is not a left-hand member. We have sectioned it here, and we're looking at a right-hand member. Now, according to Newton's, was it first law, for every action, there's an equal and opposite reaction. If there's a force going down, it's caused by the right-hand member. So the force on the right-hand member would be going up. The shear on the right-hand member is going up. And if you have shear going up on a left-hand member, then the shear, it's just the equal and opposite business of Newton's first law. No, wait a minute. That's his third law, isn't it? How's that go? The first law is, I know the second law, but what's the first law? It's a body in motion will remain in motion if there aren't any forces acting on it. Is that how it goes? And the third law, I think, says for every action, there's an equal and opposite reaction. Yeah, it's Newton's third law. But here's what you got to know. We've got a right-hand member with the shear going down. Well, that's defined as negative. So when we look up the answer in the back, the answer in the back should say the shear is negative 3.25 kilonewtons. Just for fun, let's look in the back. They're usually right about their answers. Now, this is problem 1.9. Go to the back of the book. Let's see what they said here for 1.9. We'll see if what I'm telling you is true. Having a little trouble finding this. 1.9, there we go. All right, the shear is negative 3.2, just like I said. Is there any question on that so far? We're not done yet. We just got the shear.
Griffin, can you explain just one more time, how did you get that distribution load for the small section?
Sure.
Thank you.
And tell me your name.
Mohammed.
Mohammed, yes. Yes, Mohammed. Well, I just really use some proportions, Mohammed. Let me make a little room here and I'll try to show you. We have a triangle like this, where this is 4, and if you divided it into 2, if this was 2 meters and that's 2 meters, Mohammed, this would have to be 2, wouldn't it? I mean, it's half as big, so it should be half. Did I draw that pretty good? Maybe that's a little better. This should be half of that. If you had it right here, this would be at 1 meter, 1 meter. This would be 3. This would be if you divided it into fourths, Mohammed. If that's 1 meter, that's 1 meter. This would be 1, 2, 3, 4. So far, Mohammed, are you with me on that?
Yes.
Okay. Well, where they wanted us to be was at 1.5. Where they wanted us to be right here. They wanted us to be at 1.5 So that's actually a fourth of the way. And so if you took 1.5 over 4, you get 1/4. No, that's not right. Now you got me mixed up, Mohammed. I was doing fine.
The length of that was 6 meters, not 4 meters. So that's
Oh,
why.
okay. That's my problem. Thank you so very much. Something went haywire. We've got, this is 6. Oh, no. I'll get it right eventually. This is 6 and this is 4. And if you were right here at 3, then this would be 2. If it's 3 and 3. If you divide it in half, I don't know if I divided that in half or not. It'd be more like right there, wouldn't it? Because 3 out of 6 is a half, and half of 4 gives you 2. It makes sense. Now they wanted us to go right here, though. This is 1.5, 1.5. So what that would be is 1.5 over 6. That's a fourth. Well, a fourth of 4 is 1. I didn't explain that very good. Mohammed, did you understand that now, though?
Yeah, I got it.
Good. In spite of me, he's got it. But thank you for asking. All right, good, go on. So now we know that this is what we want is 1 kilonewton per meter. Let me redraw this thing now, and we'll finish our problem. We have 1.5 meters. We have, what is it, 4 kilonewtons going this way. We have what did we decide on? I forgot. Going down. 1. Yeah, 1. No. This here is your shear. It's 3.25. These are all kilonewtons. And this was 0.75. Yeah, now I'm remembering how we did that. You got 0.75 going down, 3.25 going down. That's your shear. They add up to 4 going down. You got 4 coming up. That's what you got. Now we're in after the bending moment. Can you see that there's going to be a bending moment? This thing would spin. Can you see that it would spin? We don't spin in here. So what we're going to do is we're going to write the, what is this, point D? We're going to write the sum of the moments about D. Here we go. Well, we have a negative 0.75 times this distance here, which is, well, I think it's a half times 0.5 meters. And then we have plus 4 kilonewtons times 1.5 meters. Uh-oh, I'm running out of room now. And then we have our bending moment, plus m. Oh, gee, I ran out of room. Equals 0. The sum of the moments about point D here has to be 0. And we're going to solve that. So let me get my calculator and see what happens. 0.75 negative times 0.5 plus 4 times 1.5 equals that. And so I'm getting an M. When I solve this, I'm getting an M of minus 5.625. So the M isn't going that way, it's going the other way. It's going like this. It's 5.625 kilonewton meters clockwise on the right-hand section. But see, bending moment is always defined for left-hand sections. If you're talking about the left-hand section, the bending moment's going to have to go clockwise. It's Newton's third law again. For every action, there's got to be an equal and opposite reaction. If there's a bending moment on the right-hand section coming from the left-hand section, and it's clockwise, then the bending moment on the left-hand section, which is caused by the right-hand section, is got to be clockwise. I hope I didn't confuse you too much, but that's positive. See, clockwise is positive. Bending moments are always defined on left-hand sections. And so the bending moment should be, in the answer book, 5.625 kilonewton meters. Now let's look and see how we did. Look up the answer to problem 1.9 in the back, and we'll see if they got that right. We're looking up problem 1.9. No. Can't find it. They have P problems, which are preliminary problems. They have F problems, which are fundamental problems. And then they have the hard problems. They don't have P's or F's. They just have a number. I still can't find it. Okay, well, here we go. 1.9. They said the bending moment is a positive 5.625 kilonewton meters. That's what we got. Yay, we got what they got. All right, here's your chance to ask me anything you want about that problem. We just got it. We did it. Do you have any questions about it?
I got a question. When you're dividing it, can you choose either side? Like, obviously we choose the right side because it's a nice triangle and not the trapezoid on the left, but could you choose either side?
Absolutely. You can choose either side. Now tell me your name.
Braxton.
Braxton. Yes, you could. Now, if you had chosen the left-hand side, I'll just discuss that for a minute. It's going to be harder, Braxton, because trapezoids are harder, not much, but they're harder than, yeah. But here, just let me show you real quick. But that's a good question. Nothing wrong with that question. I just need some room to do the trapezoid. Now what we're talking about, Braxton, is a trapezoid. And this here is for kilonewton per meter. And this here we decided was, it was 1, wasn't it? 1 kilonewton per meter. Yeah, I probably need to draw that a little bit more like that. And the area of a trapezoid, I don't know if you remember this, guys, but the way it goes is, and by the way, this is, I think that would be 3.5 meters, wouldn't it? Because they're 3.5, 1.5. No, it's 4.5, isn't it? It's 4.5 and 1.5. Does that make 6? Yeah, I think so. The area of a triangle is 1/2 the base times the sum of the heights. It's kind of like a triangle. See, a triangle is 1/2 the base times the height. But a trapezoid is 1/2 the base times the sum of the heights. Okay, well, let's see. I wonder if that's right. That's I'm trying to remember stuff from whenever that was, junior high or high school. I could be wrong, but I think that's right. Now, if you do that, let's see what you get. Well, what's 1.5? What's a half times 4.5 times 5? Do you get 11.25 kilonewtons? Okay, great. Now, let's look at the forces acting on this thing. You've got, see, that's the area of it. That's the resultant. For the trapezoid, it's 11.25. And for A here, we figured that out. That's 8. So what do you have to have here? If you got 8 going up and you have this force D going up, and they have to equal 11.25, how big is D? Braxton, how big is D?
3.25.
3.25. Well, looky here, Braxton. 3.25 kilonewtons. We could have gotten that by doing the trapezoid, couldn't we? That was his idea, and it works just great. Now here, the beauty is, this is going up on the left-hand member. And remember, shear going up on the left-hand member, not memory, is negative. And so the answer is negative. They define shear going down on the left-hand member to be positive. But this shear is going up on that left-hand member. Here's your member. And so it's negative. And we could take the time and do the bending moment too, but we have other fish to fry. We're going to move on. Unless there's a comment or question, I'm listening. Okay, well, I'll ask you a question, see if you guys have been listening. And let me erase this because this is what I'm going to ask you. What I'm going to ask you is, how do you find internal loads? Let's put a question mark on that. How do you find internal loads? And let me pick on one of my very best students here. How about my friend, gosh, we have 2 Bens. There's Ben Harris and Ben Seaman. Ben Seaman, I haven't picked on you at all. Ben Seaman, how do you find internal loads, Ben Seaman? Go for it. How do you do it?
First, you gotta find external loads.
That's right.
Find equilibrium for those, and then
That's
you can
right.
break it off.
That's right.
Section of it.
He's got it. He's got it. You have to break it into parts. You have to section it. You have to take your virtual chainsaw and cut it someplace, and you have to break it into parts. That's the answer. Good going, Ben. you break it into parts. And then once you do that, then you start all over again. You draw the free body diagram in all the external forces, and then you solve for any external forces on the part that you're working on. Good going. So with that, Ben listened to what I was telling him. Okay, well, let's do some more here. Let me make a little room here, and we'll have some more fun. Anybody else have a comment or question on anything there? I'm listening. Okay, well, we're just going to do the same thing over again, only this one's, I think, easier. This is problem, this is a P1-3. P is preliminary, I think is what they call it, preliminary. In other words, it's going to be easy. It's an easy problem. Let me see if I can find it. P1-3. Well, there's the F problems. Okay, let me keep looking here. I'll find it. Anybody know what page these P problems are on? I need help.
38.
28?
38.
38, thank you so much. That helps me. I got lost. Okay, this is a P1-3. Now let me draw it. It's a cantilever beam is what it is. This is it's a fixed connection. They call this a fixed connection. That's just the name of it. And it's called a cantilever beam. That's the name of it. This thing is a cantilever beam. And they have these are external forces. There's 10 kilonewtons here, 6 kilonewtons here, and 2 kilonewtons here, and 5 kilonewtons here. And there's going to be a force there at the fixed connection. The sum of the forces has to be 0. So I need my wonderful student to tell me what I put right there. Let me pick on one of you guys. How about my friend? Hey, Noah. Hey, Noah, have I had you before in class, Noah?
Not before.
Oh, this is our first time together.
Well, I've had you on Tuesday.
Oh, okay.
Not like a semester before.
Yeah, okay. You must be in my thermo class then? Or no,
Yes, sir.
Man, I'm getting mixed up now. Oh, yeah. You're in my thermo class.
I am.
Yeah. Good going, Noah. Okay, Noah, the sum of the forces have to be 0. I don't think these add up to 0. Just a minute. Let me add them up. Let's see. And no, they don't. They don't add up to 0. So Noah, what do you have to have right here at this fixed connection? You got to add up to 0, Noah.
That's right. Let's see. Hold on. I'm adding up right now.
Yeah, take your time.
Looks like you're missing 1 kilonewton.
Yeah.
So,
So we're going to have 1 kilonewton, Noah?
right.
Which way? Going to the right or to the left over here?
You got to be going to the right.
You know what? He's right, isn't he? You have 1 kilonewton going. Good going, Noah. Proud of you. Okay, now those, though, are external. What is there? 1, 2, 3. There's 5 external forces. Those are external. And I've told you that stress is found from the internal. We're going to have to find the internal forces. Here, let me show you these equations for stress. Now, we're talking normal stress right now. There's one that goes like this. There's another one that goes like this. But we don't know how to do it. It's several chapters down the road there. But this is a normal stress that you get when you have bending. We don't have any bending going on, so we don't need that. But if you want to find the normal stress, you got to find the normal for the internal force. You understand? Now, the way you do that is the way we just did it. You have to break it into parts. So we're going to break it into parts. See, if you section this right here, broke that into parts, and you just looked at this little section right here, see where we broke it into parts there. If you have 1 kilonewton there, can you see that you got to have 1 kilonewton going to the left in here? You know what that is? That's your internal force. See, this is external, but that in there is internal. Now, if you sectioned it in here, let's look at this section in here. If you section that in there, I'll try to draw it for you here. Well, you have this 1 kilonewton here. I'm putting the external forces on it now, and you have the 5 kilonewton here. But in here, I think you got to have 6 kilonewtons compressive normal force in there. The way you find the internal loadings is you have to break it into parts. Here, let me write that. To find internal forces, now I know I've already said this about 3 times, but if you're a normal person, you don't get things the first time, or maybe even the second or third time. After maybe about a dozen times, it'll start to sink in, and you start to think, you know what? Mr. Griffin says the way you find internal forces is you have to break it into parts. You have to break into, whoops, I ran out of room there. You have to break it into parts. Okay, well, here, let's section it in here now. Here we go. Now, if you sectioned it in there, I'm running out of room here. Well, if you did, here's what you'd have. I'm probably boring you guys. This is so easy and simple, but I'd kind of like for you to get this. Now, these are the external forces. But what we're trying to find is the internal force. Let me go to one of my wonderful students here. How about my friend Samuel? Samuel, you've helped me before. Samuel, what do you have to have in here so that the forces add up to 0?
4 kilonewton force to the left.
You got it, Samuel. Good going. Excellent. See, that's an internal force, Samuel. It's internal. It's not an external. These are the external forces. This is internal. Now, what we're going to do is we're going to make a internal force loading diagram. That's what we're going to do now. Now, I gave you some homework. Let me see here. And I asked you to do problem F114. I think, just a minute, let me double check this, what I want you guys to do. No, that's not, no, never mind. Never mind. No, F111. Yeah, that's the one I want to talk about. When on your homework, guys, you're going to do some homework for me. One of the homework problems is F111. I want you to draw the normal force loading diagram we're going to do it for this problem P13 here in a minute, so you'll know how to do it. But that's part of your homework. I want you to draw the normal force loading diagram. Okay, well now we're going to do it. Here goes. Let me make some room here. This is going to be your normal force. This is going to be your x-axis. I get a drink of water here. I'm drying up. Now we decided, I erased it, but we decided that there was a 1 Newton, no, 1 kilonewton. It's compressive. It's going to the left. It's compressive, so it's negative 1 kilonewton. Not that far. It goes to where that 5 is. About to there, maybe. It's a negative 1 kilonewton. And then in here, I forget which of my students helped me on that, but in here you've got 6 compressive. So this drops down to 6. It comes over to here like this, negative 6 kilonewtons. Now what I'm drawing is called the normal force loading diagram. That's what this is. This is the normal force. These are internal. See, a normal force is internal. It's a normal force loading. Uh-oh, I'm running out of room here, diagram. Okay. Now in here, let's see, you got 6 going to the right, 2 going to the left. That makes, you need 4 going to the left, right? This thing pops up to about here. And it stays minus 4 kilonewtons till you get to here. Now we haven't done it in here yet, but if you think about it, you got 1, 5, and 6 going to the right. That makes 12 going to the right, 2 going to the left. You need 10 going to the left. So this jumps back down to minus 10. It does not go back up to 0. There is normal force inside this whole piece right here. It doesn't go back to 0 at all. You got 10 kilonewtons pushing on you here. It's not 0 right inside there. It's that. Now, if you color this, I wonder if I got any pretty colors here. Just a minute. Let me see. I don't have any. Wait a minute. I got a blue color here. Let's make this pretty. See, I'm going to color this. You know, won't this be pretty? Look. I've got myself kind of messy there. Oh, well. There it is. Ta-da! We made ourselves a pretty diagram there. We made a diagram of the internal forces. It looks like that. Okay, great. That's how you do it, and that's what I want you to do on this homework problem. I want you to draw me the normal force loading diagram on that homework problem and submit it to me on Blackboard with your, what do they call it? We were talking about that earlier, the scan camera. I don't know, you guys know more about computers than I do. Okay, well, let's move on. Is there any comment or question so far?
Yeah, actually, I have a question about the homework.
Yeah.
Are we submitting that with homework number 1? Or is that homework number 1? I'm sorry, I don't have the book yet, so I can't look and see what question number 2 on page 16 is.
Yeah, that's homework number 1. Yeah.
Okay, thank you very much. I was getting yeah.
And some of you might have already done it and turned it in, and if you have, it's not the end of the world. But that's what I wanted. I wanted you to. Well, no, that problem F16 that was homework number 1. Homework number 2 is F111. Yeah, this is homework number 2. Was that Braxton I was just talking to?
No, sir, that was Darren.
Darren. Darren, what was your question again?
I don't have the book, so I can't see where like question number 11 on page 39 is. So I was just asking what homework that was, or if it was like you're adding it to one of the homeworks.
Yeah. Now it is on page 39. You're right about that. It's on page 39. What are you going to do? Do you have a book coming, Darren?
Yes, sir. It's supposed to. It's going to be here today. I just don't have it with me yet.
See, I have a book in the library. The only thing is with this crazy virus thing, I don't know if the library is even open. I think it is. Yeah, it would be open. You could go in there and get it out of the. It's on reserve. You have to ask the librarian lady and their person, and they'll loan you my book there. Okay, well, we got time for some more fun here. Just a minute. Let's try something else. Or you can make a buddy. Find a friend that has a book. And I think you probably get the book online, or you could rent the book. or you could buy it used. There's a lot of different options there for students. And now I'm trying to remember what I wanted to do with you guys. Oh yeah, here we go. This is problem 138. We're not going to do that problem anymore. We're going to do problem 138. Now let me find it. I don't know what page it's on. Maybe you can help me here. Yeah, I found it. No, I found it. Okay, now what they've got there is they've got a board that's it's a 2x4 actually. It's a 2 inches artist rendition here. It's a 2x4. Okay. And they're going to put a 200-pound tension force on it. £200, 200-pound tension force. They want the normal shear stress in this board, but they would like for us to do it on this slant, a 20-degree slant. Well, first of all, let's just find what it would be if you sectioned it perpendicularly like this. Then internally you would have little dashed lines here. Here, artist rendition here. Yeah, that's pretty good. Can you see that if you just looked at the left-hand section where I've sectioned it, you'd have to have 200 pounds going to the right because there's 200 pounds going to the left. Now the 200 pounds inside here, that would be internal.
Hey, Igor.
Go ahead, somebody said something? Or was that just a sneeze? Anyway, you'd have 200 pounds. And so the normal stress would be 200 pounds divided by, well, it's 8 square inches, right? A 2x4 is 8 square inches. And so you would have, oh, gee, is that 50? Did I do that in my head right? 50 PSI. See, a PSI stands for a pound. It stands for a pound per square inch. Did that make sense? Did I do that right? Yeah. Is it 50?
It's 25.
Tell me your name.
Nick.
Nick, you just got yourself a thank you point. 8 into 200 is not 50, it's 25. Guys, there's hope for you. You're smarter than the instructor, so you're going to be fine. But what you've got is 25 pounds per square inch normal stress. The name of that is normal stress. Now there is no shear stress because on this section here, I'll color it for you. Let me get my blue color here again. See that area there, that blue area? There is no force parallel to that blue area. So the shear stress is 0 on that blue area. That's the shear stress. But guys, that's not what they wanted. We only have, oh, it's sad. We only have 5 more minutes together. But I think I can show you this. They wanted us not to cut it perpendicularly like that. They wanted us to cut it at a 20-degree angle. So here, let me do that. Let me just get rid of that. I don't need that blue area anymore. Okay. And I'm going to get a 20-degree angle here. Here we go. 20-degree angle. I'll just do it here. Maybe I better do it in here someplace. Okay, here we go. 20 degrees. Well, 20 degrees is right there. Oops. So we're going to cut this. We're going to cut it like that. And we're going to come in here like this. Our artist's rendition here. I probably should have drawn that with dashed lines, but you get the idea. They want us to find the normal and shear stress on that area. Well, let's just section this, get rid of all the rest of the stuff. We don't really need it. Just say goodbye to all that. We don't need all that. Now here's the thing. You've still got the 200 pounds acting on this area to the right, because the sum of the forces have to be 0 on this body. But see, this has a component going parallel to the plane and a component perpendicular to the plane. See, this is called the normal force, and this is called the shear force. Now, the shear force is 200 pounds cosine. Now, be careful. If this is 20, that's 20, cosine of 20. And the normal force is 200 pounds. It's trigonometry. It's a sine of 20. And so we're going to get that amount. Here goes. Oh, gee, I'm running out of time. It's sad. I'm getting 187 something pounds is the shear force. And the normal force, well, I can do that. No, I can't do it in my head. That's too hard. 200 times sine of 20. I'm getting 68.4 pounds. Now, let's see how we did. I want you to look up the answers to 138. Oh, wait a minute. They want the stresses. Okay. They don't want just the normal force and the shear force. They want the normal stress and the shear stress. If you read the problem, isn't that what they want? Yeah. But see, the area here is this area here. Well, it's the normal force over that area. We know the normal force, it's 68.4. But what is that area? Well, it's bigger than 8 square inches, isn't it? you know what it is? It's 8 square inches. Now here's where I'm gonna have to think and think and think. I think you divide by the cosine of 20 to get it. I think so, because see, the cosine of 20 would be equal to this distance divided by that distance. You want to call that distance, I don't know, call it x or something. It's x over, I don't know what that, wait a minute now. I don't know if that's right or not. Let me think about this a minute. See, I know what this is. It's 8 square inches. And I know what this is. It's 4 inches. Here, let's do it this way. That area is going to be, well, that's 2 inches there. It's going to be 2 inches times 4 inches, I think divided by the sine of 20. Maybe that's it. Let me think about that. Now see, the sine of 20 is 4 over this distance L. Yeah, that's it. And if you'll do that, you should get the normal stress on this area. Let me do it. Let's see what I get. I'll have to explain this better when we have more time. I'm getting 2.924 psi. Now let me do the the shear stress. Well, see, the shear force is 187.94 pounds. And if I did that right, that area there that we're interested in, that big area is 2 inches times 4 inches divided by the sine of 20. Let's get that answer and then we'll check it and we'll get out of here. Okay, divided by that times, I'm getting 8.035 psi. Now help me look at the answer book and we'll see what it says here. What is this, 138? Okay, answer book says, that probably didn't make a bit of sense. They said 2.92 psi, that's what the book got. And they said 8.03, they rounded off, that's what the book got. Well, that's one way to do it. I'll show you an easier way next time. But the moral of the story is to find the internal loading, you have to break it into parts. Well, I broke it into a part. I sure did. And I found the internal loadings. And then to find the stresses, you have to divide by the areas. Now that, you might have got lost on that, but I found that area, divided by the area, and I got the stresses. And those are the right answers. Any last comments or questions before I sign off here? Because I got another class I'm supposed to teach. Anybody? Here's your chance. Nobody? Well, say, at least say goodbye.
Thank you. Have a great day.
Yeah. Thank you. It was
Thanks.
fun.
Bye.
Bye-bye, everyone. I'll see you next time.
Right.